Today we'll be talking about the story of The Vendor Games, an epic fight to the death to find the best location for a store. I'm kidding, it's not to the death, but it is an application of Hoteling's Law, published in the Economic Journal by Harold Hoteling in 1929, which states that in many markets, it actually makes sense for producers to make their products as similar as possible. So here's how the game works. The players are two cola vendors at a beach who sell the exact same cola for $1 each. The beach has 7 regions on it, each with 100 people. All the people in a region are going to buy a cola from one of the two cola vendors on the beach. They'll buy from whatever vendor is closer to them and have no preference otherwise. If people of a region are the same distance from both vendors, each vendor will get half the crowd from that region. Each player, the cola vendors, wants to make the most money. So, where should they place their stalls at? To solve this issue, we need to understand 2 simple game theory concepts. The first is about best responses. A best response is an action the player can take that will give them the most payoff given the other player's action. For example, if Vendor 1 has a stall at location 7, Vendor 2's best response would be to place a stall at location 6. The other is a Nash equilibrium. This is a condition where each player is taking actions that are best responses to the other player. In this equilibrium, neither player can individually make a move that will increase their payoff. This is what we want to look for in the beach game, as rational people will usually use strategies that eventually lead to a Nash equilibrium. Let's start with the end cases where each vendor places their stall at either end of the beach. In this case, each vendor gets 3 full regions, and region 4 is split between them, so their payoff is $350 each. But vendor 1 could simply move to region 2, and now his payoff is $400. So, placing stalls at each end is not a Nash equilibrium, as the vendors are not best responding. Consider another case where each vendor is equally placed from both sides. So, vendor 2 is at region 3, and vendor 1 is at region 5. In this case, the payoff of each vendor is still $350, as each vendor gets 3 regions on their side, and region 4 is still split between them for a payoff of $350 each yet again. But vendor 2 could again just move to region 4 to get a payoff of $400. You may have noticed a pattern here. In these cases, either vendor could move a few regions towards the other vendor to get a higher payoff. The rational opposing vendor would anticipate that and make their move towards the other vendor, establishing a Nash equilibrium at region 4 in the center. In this scenario, neither vendor can move to another region without decreasing their payoff. A similar conclusion was derived in a paper published in the European Journal of Operational Research that focused purely on locations of the facility under the same assumptions as our beach game. Now you might understand why there are no gas stations nearby, but there are about 4 right next to each other, 5 miles away from you.